And let's dive in. Oscillations too. Oscillations are, come on. Oscillations are wiggles in a place. They've got motion, they've got potential energy. And what I would like to do briefly is let's review kinds of energy. This is really important. This not take too long. I don't want to take too long in this. I'm going to introduce energy methods for understanding oscillations. Then I want to get to our other kind of oscillation, other kind of oscillator, which is the pendulum. That's what I was demonstrating before, swinging my purse last class. So here we go. No. Before I tell you, you tell me. Question A, what is... Oh, my words. Question A, what is the equation for kinetic energy? Question B, what is the equation for elastic or spring energy? Question C, what is the equation for gravitational potential energy? Anyone who tells me QV will be mocked. Kinetic energy. Spring energy. Gravitational energy. Sammy, I don't know how you got into 112 if you didn't do 111. I think you told me about this. Can you get a break? Well, these aren't for points, but I encourage you to skim either our or the OpenStax text or Google it a little bit about energy. It's a super important topic. Lillian, the question is, A, Google form, what is kinetic energy's formula? B, what is spring potential energy formula? C, what is gravitational potential energy formula? Oh my God, and so many people have got all three right. Gerd, gerb. Gerd. Wait, I don't even see a wrong answer. The people who are answering, oh my God. Someone's mic is on. Gloria, I'm gonna mute you. Alex, you can talk. Wait, Alex is not Alex Boyce. Oh, you're muted. Unless you wanted to ask a question, in which case you are always welcome to. You don't have to chat. Okie dokie, great. People remember stuff. Yay! Most of you. I'd say probably 80% of you remember these formulas or several, 2 out of 3, which is great. I am very happy. Kinetic energy formula. The energy of motion is given by the formula 1/2 mass speed squared. Energy of motion, 1/2 mass speed squared. The energy of a spring, blink and you'll miss it. We only spent, what, a day or two on this last semester? I think. I don't remember anything. 1/2 kx squared, 1/2 spring constant times, muy importante, what does x mean? Displacement from the origin, from the equilibrium point. The origin is the equilibrium point of the spring. So if I've got a 10 centimeter spring that is currently 11 centimeters, what's my displacement? What's my x? 1 centimeter, not 11 centimeters. Yeah, it's not the length. It's how much the length has changed by it. If I've got a 10 centimeter spring that's 6 centimeters currently, what's my displacement? 4 centimeters, yeah? Ugh. Forget if I said H or Y. Mass times gravitational field times height. That's good? Yeah? You happy? Everyone happy? If you didn't have those, write these down. Okay, and what's the big idea? What's the central principle about energy methods? What's F equals ma in energy land? Energy can be transferred or transformed, not destroyed. Transferred goes from one object to another. Transformed goes from one form to the other in the same object. We're not going to have things that do work on external things. You can analyze that, and the math gets gross. No external forces other than the spring force, gravitational force. So energy is just going to slosh between these forms. You're not going to have to consider external objects. No transfer, no work. Only transformation. So the law of energy is the change in energy, change in total, is zero. You cannot change. Energy is, as we say in physics, conserved if you've got an isolated system. Energy transforms from kinetic to potential and back. And I'm only going to have either a spring or something oscillating gravitational potential oscillations. So it will transform from kinetic to one form of potential, that form of potential back. Oh, Ryan. Related? I don't think it's not identical, but first law of thermodynamics, they're related, but it's not the same. Conservation of energy is one principle. Ultimately, you can derive the law of conservation of energy from the fact that from what we observe about the universe, the time that you make a measurement does not change the measurement itself. So if I have energy, no, I don't want to go further than that. All the laws of thermo can be deduced from 1 + 1 = 2. And the probability of rolling a die is 1 over n of its sides. Anyway, almost nerd snipe me. TLDR, dead white guy, make numbers confusing. Yes, well, yes. Okay, back to this. Back to what I'm supposed to be, what I'm paid to teach you. Total energy as the system is conserved. So at all times, the total energy is equal to the sum of the individual kinds of energy, and E doesn't change. E initial equals E final. If I add up kinetic plus potential at one instant, that is equal to kinetic plus potential at another instant. Bang! We're going to apply this, but there's really not much to it. This is a mile wide, but an inch deep. We're going to be talking more about this later, so do please think about what you're doing, why you're doing it. What does it mean as you're doing it? Don't just do it to get the point. We'll make it easier next week, but yeah. Well, let's do an example. 3 minutes for D. Spring oscillator, what form of energy? Potential, kinetic and elastic, spring potential. What role does the amplitude play? What is the amplitude of a spring oscillator sliding back and forth? Distance from equilibrium, what does that appear as in those equations? X. Hint, hint, hint. Correct answers. Oh my God, correct answer. Delectable energy? Oh, lol. Okay, seconds left, minutes left. Oh, we're at 90% answering it. Okay, so here's how I think of this. I tell you the maximum kinetic energy, but I don't tell you anything about motion terms. I don't tell you about the mass. I don't tell you about the velocity. So we have to start by using the principle of conservation of energy. I want to think about the amplitude. I want to relate this to amplitude, which is the potential energy. The amplitude, when you're at a max amplitude, max position, which is the amplitude of the oscillation, your energy is all in potential form. So the first logical step here is to realize that if I want to know the maximum kinetic energy, reason about that, I could say that's equal to the maximum potential energy. So what happens if I double amplitude in the expression half kx squared? If x becomes twice as great, by what factor does this equation change? Well, if I plug in 2x, x becomes twice as great, how have I changed my expression? 2 times x squared. Nope. Old. By what factor have I changed? New over old equals 1/2 k times, you know what, I'm going to pull the 4 out front. 4 times half k x squared over half k x squared. Great Scott! According to my calculations, always wanted to say that, we quadrupled the amount of energy in the system. We have a quadratic relationship. Energy goes as the square of the amplitude. Therefore, if I double something which is squared, I get 4 times as much. If I tripled it, I get 9 times as much. Whatever factor I increase the amplitude by gets squared, and that's the ratio. Just multiplying and dividing, I can just reason about it that way. No, you don't like that. Ask me a question. No, I'm not done yet. What do you think the final answer is? Uh-huh. Yeah, exactly. So the ratio of energies is 4. What is the value of the kinetic energy? I started at 2, I quadruple it. Last I checked, 2 times 4 is 8. Yeah? Yeah, really? Yeah? For reals? Yeah? People struggled so hard with this when I started doing it this way. So when I started doing proportional reasoning, looking at a formula and reasoning how it changes without just having numbers in what was that, January, early February? No, you really feel okay about this now? Ask now or you can't urinate again. I mean, speak now or forever hold your peas. Okay, moving on. We're going to do this more in a minute. I put this in the wrong, no. Okay, so that's your very short introduction to kinetic to energy methods. As I said, you'll be practicing this more, but hey, it's an inch deep. If you know energy is conserved, if you have the equation for the various forms of energy, you can plug in and reason and stuff. There's not much more that I can tell you without just giving you all the answers. Now let's talk about a pendulum. Here's Bob. Say hi to Bob. Hi, Bob. The setup for the pendulum, as I will say on the next slide, is I've got a massless rod or a string or something that is not massless and stretchless, that I've got some ball with some mass on the end sitting out there at the end of it. I'm going to assume that the string does not stretch. So if I have something moving back and forth with a constant radius from a pivot point, that's a circular path. If you stick around for the trig stuff at the end of the lecture, I'll show you how the trig works out and you get a very nice final expression. Okay, but, and this is a big but. What we're going to discuss is not x and y, because we've got a circular motion. Aw, heck, your hearts are dropping. I can feel it. Well, I can't feel anything anymore, but I can imagine that you're feeling it. We're going to be talking about angles. We're going to be talking about the angle as a function of time. The angle as a function of time goes like this. Angle as a function of time is some initial angle cos of omega t. Oh my God, it's the same equation as with the spring oscillator. Yes, that's the point. Our amplitude, though, is not an x. Our amplitude is an angle with respect to vertical. As before, I'm going to remind you, sine, cosine, same thing. Pick the relevant trigonometric function based on whether you start at 0, go left or right, or start at right or start at left, whatever. Pick the relevant thing that describes your motion. Still, we've got an angle changing sinusoidally. Now we're going to see what goes inside this. And I'm going to hand wave briefly. I will try to keep it brief. I'm going to hand wave something funny about this, why we can do this. Okay, so I've said most of this. There are simple harmonic oscillators other than just a spring oscillator. Another important example is the pendulum oscillator. I will describe this as a mass m on the length L string, oscillates back and forth. Now I want to make a point here. What is true about the restoring force? What form of a formula do you have to have for a restoring force to have a simple harmonic motion? Slide 1 from yesterday's class. Restoring net force, what kind of function? Linear. Force must be mx plus b. Remember that? If you want signs of motion, you need to have a linear restoring force. That is to say, it must point towards the center and get stronger as you go further from away. Yeah, right? What pulls a pendulum back to the center? It's weight. Oh my sweet baby Newton. Weight is not linear. Weight is constant, right? Weight has no x. What? Weight isn't linear? This is my son when I told him. Just kidding. Okay, so I can't prove this without trig, but let me say that even though weight itself is constant, as the angle increases or decreases, how much weight is aligned with the turning angular direction does change. Let's do my example with my purse here. Which direction is weight? Which direction is turning? Left or right? Yeah, if I want to turn this, I have to push it left or I have to push it right. So the force that is down has nada to do with the turnwise direction. It exerts no torque. Remember torque last semester? Oh, the headache. Angle equals 90. Which way is weight? Which way will it turn? Which way does the force have to be to get it to move? It has to be up, down. So the closer the angle is to horizontal, the more weight acts in the direction of turning, the greater the component in the angular direction. This happens at intermediate angles too, right? It's not just all or nothing. At an intermediate angle, weight, the downward force, is partially pulling to lengthen the string. That's I'm assuming the string holds, and partly pushing it back to equilibrium. As we can show algebraically with trig and some math, the restoring force, the restoring component of weight is roughly linear. So you do get oscillatory behavior. The pendulum feels a weight component in the direction of turning proportional to angle. If you remember torque, R times F in the direction of the R. R times F perpendicular to the direction of R. Deja vu? RF sine theta. Sine is changing. The theta is changing. R is constant, F is constant, but the angle between is changing, so the torque changes. The turning amount of force. And I'm going to skip this until those brave masochistic souls stay after and we do the trig. Okay, now I have to hand wave this. I'm going to tell you that there are some gross constants that pop up, but the long story short, when you work the numbers, is that the restoring force is linear in angle. Therefore, the energy is quadratic in angle. The energy goes like the formula, and I don't remember, I'm going to have to work it out. This is the consequence of MGH plus math. Some constant C, which I'll work out after class, times the square of the angle. Yeah. It is. Well, no, weight is constant. Weight is just mg, pointing straight down. Does not change as angle changes. Yeah, gravity. Gravity. Gravity doesn't change based on your angle. No, not at all. Linear means it's y equals mx plus b. There's no slope to gravity. But how much does down align with the turning direction of the pendulum does change the angle between gravity and which way you need to push on the pendulum bob to make it turn. Yeah. It is a rotational force, and that is proportional to the angle. Math. Potential energy for a pendulum is equal to some constant, which I'll work out afterwards. It is not important. You will not be asked to calculate this, times the angle squared. Okay, you now have enough to reason through this. Ready, set, go, chop, chop, quick like a bunny. Google form answer what? C, D, E? What are we on? E. E. You stick around. You don't need it, though. Nope, it's a secret. You don't need it. Sure, set it to 1. Doesn't matter. For reasoning about ratios by factors. Don't want you to use a calculator to find. Cougar's got it. Good job, Cougar. Don't trade neighbor. Kristen, good job. Don't trade neighbor. Brian, good job. Although I wonder if you guessed. John, looks like your answer guessed. Lillian, good job. How'd your answer? Sophia, good job. So many correct answers. Not everyone. Many. Keep it coming. Keep it coming. Harley, good job. Hannah. One minute. No, we're at 90% under. Okay. What's the fundamental principle of energy conservation? This has got to be equal to half mv squared. I don't know what m is. I'm not going to tell you what c is. Actually, it varies based on length of string and stuff, and the mass, I think. But I know that the max kinetic energy and the max potential energy have got to be balanced. Yeah. Theta, angle. The angle relative to vertical. Okay, so without loss of generality, you can pick any numbers for C and M. I choose M equals 2, C equals 1. If you're reasoning about ratios, if you're talking about factors, the constants always divide out. So it doesn't matter what those constants are, in fact. Well, here's an algebra equation that's difficult to solve. Oh my God. Yeah, no, theta equals V. Now, if I put the constants back in, theta equals root, what, M1, 2C or something, ew, gross. If I take ratios, the constant drops. So what I could say is the ratio of theta 2 over theta 1, the ratio of V2 over V1 is the factor of the speed. 7/4. If something theta squared equals something V squared, how theta changes is directly proportional to how V changes. I see a question pop up. And I see Shelby enter super late. Question me. So why wouldn't our 2 be 7 squared over 4 squared? Well, theta squared equals V squared. Simplify that expression. Where's die? I chose exactly like you were saying earlier, you can pick constants in a reasoning about ratios problem, factor problem. The constants end up being immaterial. As long as you're just multiplying and dividing and squaring something, constants are ignorable. So I chose to analyze a system with 2 units of mass and 1 unit of C, whatever that. So I got theta squared equals V squared. Cancel, cancel, or square root, theta equals V. If theta doubles, so does V. If theta multiplies by, increases by 75%, so does V. Yeah, question? Nope, nope. Kinetic energy and velocity are related by square relationship. If velocity doubles, kinetic energy quadruples. Right? Because I square the V to get kinetic energy. If I square twice as much, I get 4 times as much Ke. Other questions? Any dairy farmers in here with other questions? Okay, let's move on. Now, big lesson. This will be on your final exam, almost certainly, multiple times. I've got a theme here. You can have an equation, A equals B times C, and changing B doesn't change A. To reason about physics, to reason about relationships, mathematics, thou shalt think about the meaning of A, B, and C and what affects what. Pendulum oscillations don't depend on mass, don't depend on amplitude. Pendulum oscillations don't depend on the wave, they only depend on which planet you're on and how long the string is. That's it. This is just like spring oscillators. Spring oscillators, you could have a big spring oscillation You can have a small spring oscillation. They will have the same period, the same frequency, the same angular frequency. The resistance of a resistor is not controlled by voltage. Double the voltage, you will double the current, not the resistance. Capacitance of a capacitor. Q equals CV. If you double V, you do not have C, you double Q. Think about the meaning of each term and what is controlled by what. TLDR, frequency of an oscillator is controlled by properties of the oscillator, not properties of the oscillation. Angular frequency of a spring oscillator goes by the formula root G on L. There's no amplitude in this expression. There's no frequency in this expression. I will ask you on the final, probably something like, I have a mass on I've got a pendulum of length L, swinging back and forth 30 degrees. If I double the mass of the pendulum, how does the period change? And the correct answer is nada, doesn't change. Ratio is 1 to 1, 1. Factor is 1. If you change the mass of the pendulum, the factor, the ratio of periods is 1. Does not change. 100%. No change. There is no mass in here. He is very much Martin Luther. No mass for him. Also, there is no A in here. Completely anti-Canadian. No A at all. Right? Amplitude doesn't affect the wave, the oscillation does not affect this. I'm going to give you a preview in a minute of waves. I made this point a bit for my lab sections. When you've got a wave, what controls the wave speed is not the wave itself. The wave speed is a property of the medium. The medium controls the wave speed. Wait, everyone's done this lab. Yeah, you may have seen in the lab manual, there's an expression, V for a wave on a string equals tension divided by mass density of the string. Doesn't depend on the size of the wave. It doesn't depend on the amplitude, doesn't depend on the frequency, doesn't depend on your mama. It only depends on properties of the string, unless your mama is the string. Same here. Properties of spring oscillator don't depend on the oscillation, they depend on the medium, if you will. The frequency for a pendulum is only a function of which planet you're on, gravitational field G, and the length of the string. Okay, do a problem. Oh, omega. You guys okay with omega? You remember how he relate to inversely to period? There's a 2 pi. Directly to frequency, there's a 2 pi, yeah? If angular frequency gets bigger, period gets smaller. If angular frequency gets smaller, period gets bigger. Yes, deja vu? F. This is question F. And so you don't have to type the whole darn thing out. This is choice A, choice B, choice C, choice D, choice F. Just kidding, choice C. Maybe more than one answer. Answer all that are correct. Hmm. Hmm. Many people got it right, but not, okay. So let's look at the previous equation. What affects the time, whether you measure that in frequency, angular frequency, or period, of an oscillator? Do you see mass? Do you see amplitude? No. Mass, no. Mass, no. Amplitude, no. B, C, and E are impossible. That's what I was just going on about. Okay, so do we want to increase or decrease the length of the string? Let's look at this. If L gets bigger, what happens to the frequency, angular frequency? If I make a fraction bigger, downstairs of a fraction bigger, the omega gets smaller. What I don't ask about omega in this, I ask about period. If the omega gets smaller, what happens to the period? How is period related to angular frequency? Inverse. 2 pi over t is omega. 2 pi over omega is t. So if the angular frequency goes down, what does that say about the period? The period gets bigger. Do I want period to get bigger or small? Period is too small. I want to increase it. Bang. Yes. No. I see a lot of glazed looks, a lot of furrowed eyebrows. Turn to thine neighbor and thou shalt discuss. What the hell is going on? And then ask me a question in G about physics, please. Long walks on the beach is the first answer. Ask me a question about this physics. Good, Bella. Hey, if you don't have any questions, you don't have to put in an entry. The relationship between omega and period from last class, omega equals 2 pi over t. What I remember is t equals 1 over f, or 1 over f equals 1 over t equals f. Omega equals 2 pi f. Shava, shava, 2 pi over t. Inverse. Christian asks, how does the system differentiate the weight of the string versus the weight on the string? Are you talking about the lab or about this pendulum thing? Pendulum, we're assuming the string is weightless. Are we talking about pendulums? Okay, so in the lab, as it happens, you got a thicker and a thinner string. There will be a fun phenomenon called reflection. Send a wave down and the velocity ends up changing. Some energy bounces back, some energy bounces forward. You've got an impedance mismatch. So there's something cool that happens there. How does it know is what you're asking, yeah?
Like if I attach the same string to the string, would it, you know what I mean?
So tie a 12 gauge string to a 12 gauge string? Oh, wait, what's the question? If I have the same kind of string, what? Ah, but that equation, tension over mass density, is not tension over mass. It's tension over mass density, the mass per meter. It's not mass. Uh-huh. No, same way. They have the same kind of oscillations on them. Doesn't actually matter the diameter. Yeah, yeah, totally.
Like a pool noodle and a dense string.
Yeah, totally. Kind of crazy, right? Okay, other questions. No questions. Theta equals theta initial cos omega t is describing the equation I gave you at the first bit of that. Theta equals theta initial cos omega t, describing the angle versus time for a pendulum. If you wish to, and my big point there is, how do we measure the oscillations of the pendulum? We measure it with angle. So all the stuff we've done with angle before applies. What if the same clock was on the moon? Yes, if the same clock was on the moon. If G changes, L had better change by the same factor. Alex, you get an F. I'm not telling you what his thing is. It's too terrible. Omega is inverse to period, yes. If double theta will double V. Yes, correct. I think. Okay, let's move on. There were very few questions, but I still see deadness in y'all's eyes. Waves are good, waves are great, waves are more complicated. Instead of just a wiggle in space, waves are a wiggle in space. Instead of just a wiggle in time, waves change based on space and time. Waves are oscillations the next level. And that's why we do oscillations first and then go on to waves. If you're dead, get out of here, we're done. I'm gonna do a preview, I'm gonna do some trig, but I give you my blessing. If you are dead, you have seen everything you need to do the homework. But go fast because I want to continue the next part. David. G does change very little, very little, very little. Bitte. You dead, Kendra? Well, you should just drop OChem. Just take my class. Okay, go fast. Go fast. The 3 people who are ending up staying will they need to see this, want to see this. I love your questions. Please do. You have a question? Adios.
I agree.
Or are you sticking around? Great. Hey, help me out. Who's in my lab section? Yeah. Okay. So what I'm gonna say ties into that, but you guys won't all be bored. I'm sorry I don't remember faces so well. Okay, so what I just said, an oscillation is a wiggle that happens somewhere. As time passes, something wiggles. A wave is, you got a medium instead of a single object. You've got a thing that is an extended body, and each place along that body, each place along that body can have its own wiggle. A wave is a vibration that spreads through a medium. There are a billion kinds of waves. Here are 6. Earthquakes, sound, light, radio waves, waves on a slinky, X-rays. Oh, we don't really see that. Let me say infrared light, microwave radiation. Oh, that's 7. I can't count. So the wave in an electromagnetic oscillation is not a wave of something moving up and down. It is a wave of the electric and magnetic fields. The electric and magnetic fields jiggle. Theoretically, as a light ray passes through you, if you held up an electron and looked very carefully, the electron jiggles. If you held up a compass, the compass needle wiggles back and forth. Very tiny vibrations. Light wave, unless it's stupidly intense, has a relatively low energy. And the frequency of oscillations, 1 with 14 zeros after it per second. Terahertz. Wait, is that a tera? 12. one with 12 zeros after it. Big, big, big fast frequency. So you're never actually going to observe that in practice, but it is happening as my ham radio antenna feels electric fields sloshing over it. That electric field pushes the electrons first one way, then the other way, then the one way, then the other way. That makes a slosh, which is detected by my radio. That's how a receiver works. We wouldn't call it a wave then. You could, I'd call that an oscillator, an oscillation. If it doesn't spread through a medium, I mean, I suppose you could take a little box, a mirror-lined box, and let a light ray bounce around inside there. Wouldn't call it that. I'd just call that a wave that can't escape. Fiber optic cable can go along the cable. Better. Okay, so lots of kinds of waves, and the bigio dealio, Julio, is that the same mathematics, the same physics, the same, or at least the analogous equations apply for all these waves. So the better you understand light, you've also learned something about sound. You've learned something about earthquakes. You've learned something about every other kind of wave. One of the big things, for now, we will relax this restricted later, is we're going to talk about waves that travel in one medium. And as I hinted before, wave speed is a function of the medium. So if the medium don't change, wave speed don't change. We're going to talk about uniform media. In a uniform medium, counterexample. Air is one kind of medium, water is another kind of medium. When light goes from water into air, you can reflect off the surface. I mean, you can see that. You can see the sun bouncing in the reflection in a pool of water. If you're underwater, you can work out the angles actually are different too. That's a consequence of the change in speed. Light in water slows down, does not travel at 3 × 10⁸ meters per second. Travels at, I think, 2/3 of that. So that's an example. Change the media from air to water, from air into the plastic of my glasses. My glasses could not focus light into a shape. You optometrists are going to learn butt tons about this. Light could not bend and be focused without the fact that light travels slower in this kind of plastic. Yeah. Okay. So we're going to talk about constant wave speed for now. We'll relax this restriction in the last week of content. Now there's a foundational wave equation I want to hit on here. Hey, foundational wave equation, you want to go out? No, not that kind. Distance equals rate times time. We're going to reformulate that and shuffle a term around and come up with V equals F lambda that you should have seen in the lab. Wait, anyone not in my lab? Not in 112 here? Okay, there's someone in the lecture, but it's, I don't want to make them feel bad. Okay, anyway. Let's play with this. I just said V is the speed of propagation, and that's not changing. Let's think about what distance and time even refer to. In particular, I'm going to think about one period worth of time. In one period, one full cycle of the oscillation that starts this wave, in one up and down of the wave drivers that you did in lab, in the time it takes that initial part of the string to go up and down, energy has spread out, the pattern has spread out some distance along the wave. In fact, the distance that it goes defines one wavelength, and that distance is given by the formula Vt. Distance, wavelength, equals velocity, wave speed, times period, t. We usually shuffle that around. I point out that t is 1 over f, and write v over f instead of v times t, or perhaps the most common way to write this, multiplied by f, v equals lambda f, v equals f lambda. Okay, but one last concept here, one last idea, kind of crazy here. The sine wave that is visible along a string, for instance, that is being wiggled, That sine wave is the memory of what the oscillator was doing earlier. If an oscillator starts at the equilibrium point, then a wave leaving that information leaving, well, it's starting there. The initial position of the string or spring or whatever next to it will be at the equilibrium point. Suppose the oscillator moves upward. The rest of the string is at equilibrium position, but the string or spring next to the oscillator is going to start moving up with it, right? That information is carried along the string at the speed that the wave propagates, and you're going to see that upward coming, the string come up, pass along the wave at that finite speed. As the oscillator goes back down, it will pull the string next to it back down. So the height next to the oscillator lowers. You've got a bump on the string. The front of the bump is the memory of what was happening at the beginning of the oscillation. The top peak of the bump is what is happening next in the oscillation. The bottom of the bump is what is happening next in the oscillation. If I have just one bump on a string propagating along, that means earlier the oscillator must have followed this pattern. If I graph position versus time for the oscillator, that is the exact same picture as height versus position along the wave, along the string. What do you mean? Yes, 100%. The motion of the string is vertical. The motion of the string is vertical. The up and down speed of the string is not what I'm talking about by this V.
But when you're saying what happened before it, it's a memory going across. What happens if you record memories faster than you can send them? I guess what I'm saying.
So if V is not infinity, whatever I'm doing here, however fast my velocity is here, if it takes more than an instant, that finite V will move the pattern out along the string. It's impossible to have the pattern not match up with, I think if my intuition and memory are serving, it's possible to have the pattern not move like the string is moving. Could be wrong about this. If I am wrong, look up, you can Google this, group velocity versus phase velocity. But I think I'm right. Okay. Yeah, this is easy. Yeah, this is easy. I'd rather go to the trig. Who's staying for trig? No, who's going for trig? Okay, you're going? Get out of here. Love you, but go. No, staying for trig or going? Staying for trig? You don't want trig? How well do you, okay, so TLDR, that's the intro, the brief. You're going, you're escaping. Okay, that's okay. That's my brief intro to waves. Much more next week. Don't skip next week because you've learned it all. No. Okay. Now I would like to hit on what? Yeah. Yes. Good. Okay. Now, trig, let's understand the pendulum better. Are y'all okay if I review angular crap for a second? You need it. That's right. You do need this stuff. Okay. So katoa. Foundational law, the law, laying down the law of angular dynamics is that force equals mass times acceleration, except force becomes torque, mass becomes moment of inertia, and acceleration is angular acceleration. Torque has its equation. The moment of inertia has its equation. And alpha is related to ordinary acceleration by okay, let's talk about each term. Torque R in torque has a particular meaning, which is not always the same as the size of the circle or whatever. This R is defined, this is called the moment arm, is defined as the distance from the pivot point to where the force is applied. You can find a torque of every force. Every force will have a different moment arm. F is force, duh. The angle also has a precise definition. It is the angle from the moment arm's direction to the force's direction. For instance, let's do each of these terms as we go along. Here is a, oh, for dog's sake, here's a pendulum. Oh, for Bob's sake. Yeah, for Bob's sake. This is Bob. The pendulum has a force on him, 2 forces actually, but the tension force does nada. Tension force is just radial, not in the angular direction. So here is weight. Here is the direction of weight. Oh, I drew him. If this is the pivot point, here's the ceiling. If this is the pivot point and that's the weight force, here is, oh, why is such a bad vector? Here is the R vector. Here is R. It is the distance and direction, incidentally, from the pivot to where the force acts. That is the theta in RF sine theta. Let me think of an example where R is not the size of the circle it makes. Oh, screw it, no. Never mind. Okay. R is not always the size, the radius of the path. Really. No. The definition of R is where is the pivot point, where is the force act? Ha, ha, ha. I'm going to push on a door. I'm going to push on its middle. R is this length. I will exert less torque if I use the same force. Oh, I don't even open the door at that distance. At this R. Smaller moment arm, less torque. Same force, less torque. Same force, oh, that's quite easy. If I increase the moment arm, and in that final case, it was the size of the circle subtended. The increased moment arm means I got a bigger torque. Okay. Sorry. Okay. I, moment of inertia. Moment of inertia. Don't just call I inertia. Inertia is different. Inertia is a principle, not a quantity. Is some constant, which I call the shape factor, that's the Greek letter beta, times the mass of the object times the size of the object, which is not always the radius of the object, is a characteristic size. For a cube, you might have the side length. Don't have to have round objects. I like round objects, mostly because donuts are round. Beta reflects how mass is distributed in the object. Suppose I've got a wheel. If all the mass is at the hub of the wheel, it's called the hub? No. It's called the wheel of the wheel, the tire. If all the mass is on the tire, if I've got a massive tire and the spokes and the hub is the middle, right? Spokes and the hub are small. Beta is 1. All of the mass is at the outside. Suppose I've got no tire on the outside and a honkin' big spokes, or the inside axle is some Mondo axle. That is much easier to spin because all the mass is concentrated where the circle of motion is tiny. If you stand at the center of a merry-go-round, you are contributing nothing to its moment of inertia because you're not moving. You're just rotating in place. If you're standing on the edge of the merry-go-round, well, it has to do some work on you to move your mass. So beta is a shape factor. You can't calculate him without calculus. I will tell you for a pendulum bob, beta is 1 because all the mass is at one place, the full length of the rod. Finally, alpha. Alpha is the rate of change of omega. Omega is the swing rate, how the angle is changing for the rod. So let's put these puzzle pieces together. R, in this case, is the length of the string. F is mg. Sine theta is sine theta. Note, this theta is the same as the theta of the pendulum, how we define theta, the angle with respect to vertical, because vertical angles are congruent. Not vertical angles. What's that called? Opposite. What's it called? Two parallel lines cut by a transversal. Oh God, Mrs. Stone would be so upset with me. I don't remember 30 years later. Two parallel lines cut by a transversal. These are opposite interior angles. What's that? Oh, whatever. You guys remember geometry class? Okay, so this angle, the angle of that I specify, the angle that I care about of the pendulum is the same as this angle. It's the angle between vertical and that diagonal line, yeah? Okay, so this angle I can use theta for. Tau equals I beta, which is 1, I said, for this system. If you've got a massive rod, if you've got a physical pendulum, like for instance, my arm swinging back and forth, the beta is complicated. The motion gets more calculationally exciting, let me say. Times, now I say alpha is related to the acceleration of the object by a over r, and r is L. So the acceleration in the angular direction, looky looky, L on the left, L squared over L on the right, M on the left, M on the right. The acceleration in the direction at right angles to the motion, the direction parallel to the motion, the direction along the angle, direction of the rotation is g sine theta. No, they're not interior. That's interior. Oh, yeah, the g thing. Okay, so we see that the force, well, force is mg sine theta. Screw it, whatever. The acceleration proportional to the force is proportional to the angle. Oh, sine theta. No, this isn't a linear restoring force. I lied. But, and this is a big but, take out your calculator real fast. You guys have calculators handy? Put it in radians mode because we ain't no stinking engineers in here. I want to do a little experiment. Suppose I am dealing with small angles. Angles much less than 90 degrees. Tell me, what's the sine of 0.1? Small oscillation. What's the sine of 0.1 in radians? 0.09. Oh, I can't write that down. 0.099, I'm going to round to 0.1. What is the sine of 0.01? Oh, rounding a little, yeah. Sine of 0.001. Round. Oh, my sweet baby Newton. Sine of theta, if you're measuring in radians, is equal to theta. That actually could save your butts on an MCAT. Here's a method for approximating sine. Sine of theta is roughly equal to theta measured in radians. You need to know 57.3 degrees is a radian. You need to know that this doesn't work if you get big. Tell me what sine of half is. Damn it. Yeah, if theta equals half a radian, 30 degrees, what's sine theta? 479. sine of 1 radian. Sine of 2 radians. Oh, that's not the same. So this is true if you're dealing with angles small. But hey, what did I say earlier? I'm going to say, no, we're not going to analyze this swing. This swing is not actually, simple harmonic motion. But as long as you're dealing with a subtle, simple swing, we can approximate sine theta as theta. In that case, A looks like G theta. Linear equation! Bam! No, sorry.
Like 1-to-1 at first.
The slope of sine, what's derivative of sine? Cos. Cos. The slope of sine is the cos function. Kind of magical. What's cos of 0? The slope of sine at the origin is 1. So they start out exactly lying on top of each other. Now, sine is not actually 1. Sine is a complicated function. Exactly parallel.
Sine 0 and cosine 0 are very different. Right?
Sine of 0 and y equals x. Y equals sine of x and y equals x look the same. Try it. Zoom into your calculator, set your window as like negative 0.1 to 0.1, and graph sine of x and graph x. Sine of x is just, looks like a straight line with constant slope. The slope 1 even. There is a fun little formula. What cost? Here's a really good approximation of sine. As a 7th order polynomial, we are approximating sine as sine theta equals theta. You want more precision? Oh, Peter's saying, Andres. You want more precision, you could throw in the, what is that called? Cubic term. Theta cubed over 6. Try it. Graph theta minus theta cubed over 6. That will agree much more closely. For instance, tell me what theta minus theta cubed over 6 is when theta equals 0.5. I bet dollars to donuts it'll line up with 0.47 closer. What is that? 0.5 minus 0.5 cubed over 6. 0.48. Try plugging in with plus theta cubed over 120, if my memory serves. Theta fifth over 120. Oh, I should get some more sig figs on sine of 0.5 itself isn't exactly 0.47. What's he for reals? .4794. And what's the God damn it, it's not the cubic term. Theta minus theta cubed over 6, not just 0.48, 0.48 what? Okay, so you can see this is approaching. These are getting close to, actually that overshoots, what the hell? I might have gotten the 120 wrong. Whatever. So 0.5, sure, then you add more terms on it, it gets quite close. Oh, magic. This is called the Taylor series, by the way, and engineers learn about Taylor series as an approximation method for god-awful functions they can't deal with. I mean, physicists do this too, but if you mention Taylor series to an undergraduate in engineering, they will usually blanch, maybe vomit, maybe pass out, because your first encounter with this, no one understands this on their first encounter. How to generate these. Huh? I think, if I recall correctly. You should look, zoom in, and, well, zoom out, and you can see that it matches the curvature of sine closer and closer. How good are you in calculus? Do you remember what derivative of x squared is? Okay. Product. Power. Bring down the 2. Subtract 1 from the power. 2x. What's the derivative of x cubed? 3x squared, right? Okay. These ultimately derive from using that power rule again and again. Oh, do you remember derivative of sine is cosine, derivative of cosine is negative sine? The negative is why these are minuses. The positives are the alternating cosines. Come to office hours sometime, and your brain should be probably a little bit full right now. We can deduce the master expression for any Taylor series. You can do it. If you remember that much of calc, you can do it. It's fun. These are factorials, by the way. Factorials of the odd numbers. Okay, my wife will kill me if I don't go home and take care of kids. So let's stop here.